Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, we are group FA3 from OS class section 3. And for our project on designing operating system solution for real world scenarios, we choose e-commerce system. Okay, so we're describing our selected scenario. Okay, our target environment is a high traffic business to consumer e-commerce platform that are built to host hundreds of thousands of concurrent users simultaneously. And our peak demand scenario is occur during midnight flash sale, where massive traffic will surge and create an immediate bottleneck of a million incoming threads at a single point in time. So this forces the OS to concurrently handle two competing workloads. The first one is the interactive mix, which is the fast, high priority user action, like loading product pages or clicking buy now. And the second one is the background mix, which is compute heavy, long running batch process, like automating inventory update. So if these two left unmanaged at the OS layer, it will create an intense traffic concurrency and will introduce another thread. The thread that they will introduce is CPU thrashing, where the processor will face a severe risk of wasting cycle that switching between thread instead of processing orders. And the second thread is that it will create address space protection risk, where strict memory isolation is needed to protect volatile users states or private payment credentials. And the third one is a disarm contention, where a massive surge of synchronized write requests that are targeting identical storage simultaneously, that will causing physical head thrashing. So our goal here is to ensure low latency, high availability and strict data consistency under this extreme condition.
Our group chose a microkernel architecture instead of monolithic system. The main features in this design is minimal core kernel, which is handles basic hardware tasks and communication between processors, which we call IPC, and all other large services like our database, network, and file systems run completely separately in the user space. The biggest benefit of this design is fault isolation. For example, during a big midnight flash sale, thousands of people will search for products at the same time. If our catalog server crashes from too much traffic, the crash is trapped inside its own user space box. The core kernel and the payment systems keep running perfectly without any interruption. The OS can just restart the catalog server by itself, keeping the website online when matters most. For CPU scheduling, we chose multi-level feedback queue to separate agents transaction from sender browsing. There are three queue structure. Q0 high priority, round robin with 2 milliseconds time limit. Q1 medium priority, round robin with 8 milliseconds time limit. Q2 with use first come first serve. Process dimension move long and non-urgent tasks down to keep the payment fast lane open. Aging mechanism, scheduling promotes waiting background tasks to prevent starvation during long sales. For trade-off analysis, we reject first come first serve and round robin because of the convoy effect and context switching thrashing. So we choose MLFQ because it protects important customer payments while keeping background tasks moving.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faiz bin Muhammad Fauzi, metric number 2419753, and I'll be presenting on the strategies for both memory management and the scheduling. For memory management, we chose segmented paging with demand paging. Think of it in two parts. Segmentation divides the application into logical sections, like a separate zone for payments, Shopee cart, and another for browsing. So next is demand paging. So demand paging makes it more efficient. Instead of loading everything into RAM at once, it only loads what's actually needed at that moment. So next we have the architectural mechanism. So these two mechanisms work together through three key operations. So the segment tables enforce strict isolation and protection. Then we have the page fault handling that loads missing data on the fly in milliseconds. And lastly, the LRU-based reclamation instantly cleans up memory when sessions end, preventing memory leaks under heavy traffic. So in short, segmentation keeps the data secure, while paging keeps the memory efficient. Moving on to this scheduling strategy. For this, we chose priority-based deadline C-look scheduling. This hybrid scheduling algorithm splits all these requests into two queues. Critical writes like payments go into the high priority queue, while everything else, catalog reads and browsing, goes into the low priority queue handled by standard C-look. During each sweep, any write approaching its deadline gets injected into the active path immediately, skipping the read queue entirely. So, reads stay efficient and critical writes are always committed on time, no exceptions. That is all from me. I'll now pass the presentation to Brother Afab. Thank you.
Moving to the last part, integration of the components and final design. This is the overview of OS strategy architecture that we are using. Starting from user make request by. As shown, microkernel is preferred over traditional monolithic as it creates an isolation of web browsing functions in a critical operation by secure routes via IPC. In a simple words, if one component fails, the system remains isolated and continue other transactions as normal. After that, transaction server will create critical checkout thread and pass to the three subsystems under OS layer. This system will be working and operate supporting one another. First, MLFQ CPU scheduler is chosen and it will check if the thread is a critical transaction or not. If it is, it will flag it as Q0, which is the highest priority and guarantees its execution over other processes. If it is a background browsing request, it will flag to priority 1 or above. Next, memory manager proposed in the architecture is the segmented paging, whereby it will only load the exact data needed instantly into the secured RAM. This allows to maintain RAM efficiency while protect customer payment details. Finally, the CLOOK this input-output is connected to the layer functional by placing the right command into a high priority queue, preventing from this to buckle under massive read or write. The disk will switch in one single direction smoothly. The mechanical lag of disk head thrashing will also be able to be avoided this way. In conclusion, this OS layer architecture proposed introduced to us more context switching overhead than the standard OS. Theoretically, it should provide the strict transactional consistency, high availability, boosting performance while maintaining data security without failing the e-commerce transactions. That's all from us. Thank you.